Hello everyone, I'm Jason Polakya and welcome back to Keymaker channel. In this episode of Hacking the ECE Board Exam series, I will discuss satellite carrier to noise and carrier to noise density calculations using JMA's shortcut formula. Again, if napanood nyo na yung mga previous episode, ang goal natin sa board examination is to answer as many as we can, as quickly as possible. That's the goal. Because we don't have the luxury of time na magbabad sa isang question. Imagine, you have only 4 hours per subject, in this case, EST. So 100 yung questions and you have 4 hours. That's roughly 2.4 minutes per question. So we don't have the luxury of time na magtagal sa isang question. Ang goal natin is to know the most probable answer as quickly as we can and then we jump to the next question. Yun yung goal natin. And kapag mayroon pang time, pwede natin balikan yung questions and let's try to verify it using the longer method. But for the meantime, sa first halimbawa sa board examination mo, ang goal mo, yung initial part is to answer as many as you can. And then, balikan mo na lang kapag halimbawang madami ka pang time para i-verify yung mga questions. Now, pag-usapan na natin yung sa satellite communication. So, let's go to this one. First, let's discuss yung carrier to noise ratio. So, the formula for carrier to noise ratio is, nakikita nyo naman sa presentation. So, this is the formula for the carrier to noise ratio. That's equal to the transmitter power. This one is the ideal formula for, ito pa yung hindi pa natin masyadong kino-consider yung iba pang mga klase ng losses. But in this formula, the transmitter power is in dBW minus the transmission line losses. Madami kasing mga klase ng losses eh. In this case, for example, meron tayong earth station and then meron tayong satellite. So this one is from earth station to satellite. So this one is uplink communication. And this losses here, that includes, madami yan eh. May tinatawag tayong branching loss, meron tayong feeder loss, may coupling loss, may back-off loss. Collectively, let's just call it as yung mga transmission line losses. And then, plus yung tinatawag nating transmitter antenna gain. Collectively, itong tatlo na ito, yung transmitter power, and this miscellaneous loss, or yung total transmission line losses natin, plus the transmit antenna gain, collectively, we call this one as the effective isotropic radiated power. And then, during propagation, yung atin pong signal, makaka-experience yung tinatawag nating attenuation. And this one is, hindi pa natin kinoconsider yung ibang klase ng, this one is due to distance and frequency alone. So, yung attenuation natin, o yung tinatawag nating free space loss, in this case is 92.4 plus 20 log ng frequency in gigahertz plus 20 log ng distance in kilometer. So take note that this constant here is only applicable or gagamitin mo lang ito pag yung frequency mo is in gigahertz. So for example, the frequency is 12 gig. So ang gagamitin mo value dito is just 12. And then if the distance given is in kilometer, take note of those constant. Then we have here yung tinatawag nating G over T. O this is called as the satellite's FOM o yung satellite figure of merit. Yung mag-determine yung performance ng isang satellite, yung kanyang FOM is called as G over T. Madaming klase kasi ng mga tinatawag tayong figure of merit eh. For example, sa amplifier. Ang amplifier, meron po siyang tinatawag nating figure of merit. Siya yung magdidictate kung maganda ba yung amplifier. Pag tinanong ka sa board exam, ano ba yung FOM ng amplifier? Kung mamimili ka between the 4. So, mayroong 20 dB, may 30 dB, may 40 dB, may 50 dB. Pero hindi pa kagad, pag pag-uusapan natin, ampli, hindi kagad gain ang magdedetermine kung maganda ba yung isang amplifier system. Ang magdedetermine o yung tinatawag nating FOM ng ampli is yung tinatawag nating gain bandwidth product. So, imumultiply mo yung value ng gain doon sa kanyang bandwidth response. Pag nakakuha ka ng pinakamalaking value, for example, ang gain niya is 30 dB at ang kanyang frequency response is nasa, for example, 100 MHz. So pag pinag-multiply mo yon, that will give you the gain bandwidth product. And sa 4 choices sa board examination, yung magbibigay ng pinakamalaking value, that's the best type of amplifier. Yun yung sa ampli. Yan yung kanyang FOM. Sa fiber optics, yung optical fiber natin, ang magdedetermine kung maganda ba yung isang optical system is yung tinatawag nating distance or bandwidth distance product. So sa optical system, sa optical fiber, ang magdedetermine is yung bandwidth distance product. Madaming klase. Sa radyo naman, for example, sa isang radio receiver, pag mamimili ka, pag check mo kung alam ba yung magandang receiver, so ang magdidictate naman is yung tinatawag natin kanyang noise figure o noise factor. So yun yung mga iba't ibang klase na tinatawag nating FOM. So for satellite, ang FOM niya o yung maganda ba yung isang satellite system, that is by means of yung kanya tinatawag nating gain over temperature ratio or G over T. That's the satellite FOM. And then, plus 2 to 8.6. So itong 2 to 8.6 na ito, in dB, that's the dB equivalent of the Boltzmann constant. Yung Boltzmann constant, which is, ano nga uling bali nun? That's 1.38 times 10 to the negative 23 joule per degree Kelvin. So pag kinuha mo yung dB equivalent niya, ito po yun, that's 2 to 8.6. And then plus 10 log ng bandwidth. So ito yung formula ng carrier to noise ratio. Take note, pag-usapan muna natin. Meron tayong analog system at meron tayong digital system. So, pag-uusapan natin between the two, yung magdidictate ng noise performance ng isang system, sa analog system, we have what we call as carrier to noise and carrier to noise density. But for a digital satellite or digital microwave system, we have what we call as carrier to noise and energy per bit to noise density. So, kung napansin nyo, pag analog system, carrier to noise and carrier to noise density. But for pag digital system, carrier to noise and energy per bit to noise density ratio. So yung noise performance ng isang analog system is basically pag nakita mo yung kanyang carrier to noise density ratio. Yun yung magdedetermine ng noise performance ng isang analog system. Yung digital system naman, ang noise performance niya is typically expressed in terms of what we call as energy per bit to noise density. So, hindi naman yun yung topic natin. Balik na tayo muna dun sa carrier to noise and carrier to noise density ratio. Yun naman pong carrier to noise density is basically carrier to noise ratio relative to a 1 Hz bandwidth. Yun po yung tinatawag nating carrier to noise density. That is simply the carrier to noise ratio relative to a 1 Hz bandwidth. And take note, iba din po yung tinatawag nating carrier to noise ratio sa signal to noise ratio. Yung carrier, ang pinag-uusapan natin dito, from the name itself, carrier, this means this is a signal na nasa modulated stage pa. Wideband pa yung ating signal dito. Pag nag-undergo na siya ng demodulation process, yun na po yung tinatawag nating signal to noise ratio. Yung noise performance ng isang radyo, once the signal is demodulated, is called as signal to noise. Pag hindi pa siya na-demodulate, yun yung noise performance ng radio, which is yun yung tinatawag nating carrier to noise performance. So in this case, ito yung formula. And yun naman pong pangalawa, pag-uusapan natin, yung carrier to noise density ratio naman, is kung napansin nyo, same lang, ang pagkakaiba lang is wala tayo ng bandwidth dito. So wala dito yung bandwidth. So this is simply the EIRP, this three here, collectively called as EIRP, minus the attenuation due to the distance involved and frequency, plus yung ating FOM in dB, plus the Boltzmann's constant. So, plus 2 to 8.6. So, yung dalawang formula na yan, kung babalikan natin, medyo hindi naman siya ganong ka-burdensome na kabisaduhin. But unfortunately, kapag nagpe-prepare ka na sa board examination, magpa-pile up na yung mga formulang kailangan mong intindihin at kabisaduhin. Kasi mas maganda, hindi lang kabisado mo yung formula, much better, naiintindihan mo yung ibig sabihin ng formula. But unfortunately, sa board examination, we have 4 subjects, mathematics, electronics, JAS, EST. So, nagpa-pile up na sa utak mo yung formula. Libo na yung formula ang kailangan mong kabisaduhin. And itong formula na ito, isa sa pinakamahabang formula na mai-encounter nyo sa ECE Board Examination. And kahit nga maikling formula, pag sobrang dami na at nagpa-pile up na sila, medyo mabigat na din yun sa isip. Especially, itong napakahabang formula na ito. Kaya, here comes yung shortcut na ginawa ko. And again, to manage your expectation, itong shortcut formula na ginawa ko, meron din tong fallback. Meron tong trade-off. So, sabi natin, meron siyang, kahit pa paano, this is just an approximate formula. Meron siyang margin of error na mga more or less plus or minus 3 to 4 dB. Hindi siya ganun na exact makukuha mo yung tamang sagot kasi this one is just an approximate formula. A little trade-off. You want the longer formula or this shorter one, meron lang konting trade-off. And sa board examination naman, gumagawa din kasi ako ng question eh. So, as a teacher for more than 10 years, pag gumagawa ako ng mga questions sa exam, and minsan sa sobrang dami mong ginagawa, pag madami ka pang gagawing ibang trabaho, pag gumagawa ka na ng question, so nakuha mo yung sagot. For example, the answer is 40 dB. Minsan, magmamadali ka ng gumawa ng mga random choices eh. 40 dB yung tamang sagot, so ang gagawin mo, 40 dB, 50 dB, 60 dB, 70 dB. Random na lang yung ibang mga pampagulong kumbaga choices, but your answer is 40 dB. And kung pag-uusapan din naman, pag naka-dB na yung mga value, hindi pwedeng ang tamang sagot mo is 40 dB, then ang mga ibang choices mo is 40.8 o kaya 40.5 o 41.2. Pag masyado magkakalapit yung choices, lalo na pag naka-dB, medyo hindi ganun ka-accurate yon. Dahil alam naman natin na pag nagko-convert ka na into dB, yung 0.1 difference lang, medyo sa, for example, yung 1 dB at yung 1 in dB at yung 1.1 in dB, so medyo may difference na yun eh. Kaya normally dapat, pag gagawa ka ng choices, kung alam mo yung nagaganap during kumbaga formation to dB, dapat kahit pa paano magkakalayo yung choices mo. But, puntahan natin ito. So, the carrier to noise formula na ginawa ko is, ito yung shortcut, is approximately equal to the EIRP plus the figure of merit minus 36 dB. So, yun na lang yung kailangan natin tandaan. So, ang carrier to noise ratio is minus 36 dB. But for carrier to noise density ratio, plus 25 dB. Kung bakit minus 36 and plus 25, hindi ko na ma-discuss in full details. Kasi medyo haba tayo ng gusto eh. I want to, kumbaga, limit itong video na ito. Kapag diniscuss ko pa kung bakit minus 36 dB and plus 25 dB, hahaba ng gusto yung discussion. But I prepared 4 questions here. Pag-usapan natin yung 4 na question na yan. So, let's start with this one. So, itong question na ito, nakalimutan ko na kung saan ko siya kinuhang textbook. So, but let's try to answer yung question number, 13. Itong book na ito, meron siyang number 12 na nagpapahanap ng carrier to noise density. At yung number 13, pinapakompute din yung carrier to noise density. And since ang may sagot, mabe-verify natin yung tamang sagot doon sa yung odd questions lang ang may tamang sagot. So, itong number 13 here is 100 dB. So, simple itong tanong na ito eh. You could easily compute for the carrier to noise density ratio. Kuha tayo ng calculator. So, ito yung calculator natin. I-compute natin to. Pag yung formula ang ginamit natin yung mahaba, hindi ko na siya gagamitin ha. I'll just use yung shortcut formula ang ginawa ko. Sabi natin, pag carrier to noise density, ano yung gagamitin natin? That's simply the effective isotropic radiated power plus the G over T and plus 25 dB. So, ang EIRP niya dito is equal to 46.5. So, 46.5 plus yung ground station figure of merit is 30.7. So, ang given dito tatlo, EIRP, free space loss, and yung figure of merit. At yung binabanggit ko sa inyo, may mga cases kasi sa board examination na ang ibibigay sa'yo is yung jargon. In this case, the FOM or the figure of merit, hindi yung G over T. So, kabisado mo man yung formula, pero hindi mo alam, yung palang FOM, yung figure of merit, is yun yung tinutukoy na G over T, problema yun sa examination. So, dapat alam mo din yung ibang mga jargon o yung ibang mga term doon sa ating pong mga, halimbawa, sa mga formulas. So, in this case, so 46.5 yung EIRP natin, plus i-add natin yung FOM, which is 30.7. And then, sabi natin, plus yung constant. This is 25 dB. So the answer is 102.2 dB. So ang approximate solution, ang shortcut formula na ginamit ko is yung JMA's formula. Ang nakuha natin sagot ay 100.2. Ang sagot doon sa textbook is 100 dB. So, merong 2 dB difference, but that's tolerable. Pag nagko-compute ka sa board examination and then ginamit mo yung shortcut formula, nakita mo na may closest answer. Halimbawa, ang closest answer is letter C. Jump ka na sa next question. Balikan mo na lang siya using yung standard method. So, yan yung sa first question. Now, let's jump to the next question. Ito naman, itong question na ito is galing naman po sa, I think sa Blake po ito. Pinicturean ko yung sa Blake. So, sabi daw dito sa problem na ito, the receiving installation whose G over T was found in example 20.5. So, this is example 20.7. Yung previous example, pinapakompute dun yung G over T. So, more or less, gagamitin na lang natin dito yung value ng G over T is used as a ground terminal to receive a signal from a satellite at a distance of 38,000 kilometers. The satellite has a transmitter power of 50 watts and an antenna gain of 30 dBi, or dB relative to an isotropic antenna. Assume losses between the satellite transmitter, ito yung sa second page, o sa next page, and its antenna are negligible. So, wala daw losses. The frequency is 12 gig. Calculate the carrier to noise ratio at the receiver for a bandwidth of 1 megahertz. So, ito naman is, baliktad naman ito. This is from the satellite to a receiving earth station. So, this one is downlink transmission. So, ang pinag-uusapan dito, yung satellite has a transmitter power of 50 watts. And the antenna gain is 30 dBi. At yung distance between the satellite and the ground station is 38,000 kilometers. Assuming walang masyadong losses and the frequency is 12 gig, pinapakompute yung carrier to noise ratio sa ground station for a bandwidth of 1 megahertz. So, pinakita dito yung calculation. Yung earth station, ang G over T niya is 20.6. Yan yung sa previous example, sabi daw sa problem. So, whose GT was found in example 20.5. So, in this particular example, ang G over T niya is 20.6 dB. Now, we could compute for the satellite transmitter power in dBW. That's simply 10 log ng 50, which is 17 dBW. And then, we could compute for the EIRP. The EIRP is simply the transmitter power in dBW plus the antenna gain in dB, less any losses. So, in this case, negligible naman daw yung loss. So, the EIRP is 17 dBW plus 30 dBi, and that's equal to 47 dBW. Now, yung next is, papakompute dito yung free-space loss. Kasi that's part of the formula. So, yung free-space loss, ang ginamit niya equation is 32.4. Yung ginamit natin kanina is 92.4. So, ang ginamit niya is 32.4 plus 20 log ng distance. So, ang value for distance niya dito is 38,000. Pag ang ginamit mong constant is 92.4, just use 38 instead of 38,000. So, makakatipid ko pa ng konti na sa pagpindot sa calcu. Baka masobrahan ka pa ng 0. So, instead of using 32.4, you could use 92.4. So, 92.4 plus 20 log 38 plus 20 log ng 12. O kung gusto mo sa bilis, that's 92.4 plus 20 log ng 38 times 12. And the answer for this one is 205.6 dB. Yung loss due to attenuation. So, this one is for free-space condition. Then, sabi daw dito, there are no miscellaneous losses. And since the receiver feed line loss was already considered in the calculation of G over T, dun sa previous example, we can now compute for the carrier to noise ratio. So, pag kinuha natin yung carrier to noise ratio, the answer is 30.6 dB. So, that's 47 dBW minus 200.6 dB for the free-space loss plus 20.6 dB for the satellite FOM, yung figure of merit niya, or in this case, the G over T, and then the Boltzmann constant, that's 2 to 8.6. And then, minus 10 log na bandwidth. Baka makalimutan nyo, ang pinapakompute dito is carrier to noise. So, present yung bandwidth sa equation. That is 10 log ng 1 megahertz. So the answer is 30.6 dB. And I think past board exam na ito Nakopya na yan in the past. Lumabas na yan sa board examination. Now, let's try to compute this using yung approximate formula na ginawa ko. So, using the JMA's shortcut formula. Ano nga ulit formula natin? That's simply EIRP plus the G over T pag carrier to noise minus 36 dB. Balik natin yung formula. So, ito yung formula natin. So, pag carrier to noise, that's EIRP plus G over T minus 36. So, all you have to remember is the constant. Pag carrier to noise lang ang pinapakompute, minus 36 dB. Pag carrier to noise density, plus 25 dB. Kung paano nakuha yan, saka natin pag-usapan yan sa ibang discussions na. Now, balik tayo dito sa ating sinasolve. So, this is also a past board exam. Halos lahat na ng questions sa Blake na encode na yon at madami na naglabasan doon. And ito is also a past board question. So, gamitin natin yung formula ng ginawa ko. Sabi natin, EIRP, which is 47 dB, plus the satellite G over T, which is 20.6. So, plus 20.6. And then, plus, this one is minus yung constant natin, which is 36 dB. And the answer is 31.6 dB. Yan yung carrier to noise using yung JSON's or JMA's approximate formula. So, ang sagot sa board exam is 30.6. Ang sagot ko is 31.6 dB. So, pag nakita mo yan sa board exam and then sinolve mo using approximate formula, wala pang 10 seconds yun Nakuha mo na yung halimbawa. Magkakalayo naman yung choices. Sabi ko nga sa inyo kanina, dapat ang choices, pag naka-DB, pag gagawa ka ng choices, yung mga magagandang choices, yung maayos na choices, dapat somehow i-consider mo yung pag-transform from unitless to DB. Dahil pag nag-DB ka na, pag nag-log ka na, then nag-multiply ka ng 10 or ng 20, medyo may konti ng discrepancy. Halimbawa, nag-round up ka. Kaya, yung 30.6 and 31.6, may 1 dB na margin, that's tolerable. So, pwede na yan sa board examination. Now, punta tayo sa next question. Itong next question is again galing sa textbook. So, mag-compute tayo dito. In a linked budget calculation at 12 GHz, the free space loss is 206 dB. The antenna pointing loss is 1 dB, and the atmospheric absorption is 2 dB. The receiver G over T ratio is 19.5 dB per degree Kelvin, and receiver feeder loss are 1 dB. The EIRP is 48 dBW. Calculate the carrier to noise spectral density ratio. So, pinapa-compute. So, in-screenshot ko yung galing sa isang textbook din. Popular textbook din do sa EST. So, now, ang sagot doon sa textbook is 86.10 dB Hertz. Ayan yung sagot doon na carrier to noise spectral density. Let's try to compute this using our shortcut. Sabi natin, pag carrier to noise density, that's simply the EIRP, which is 48, and then plus the G over T, which is 19.5. And then, pag carrier to noise density, sabi natin, just add 25 dB. So, this is the answer if you will use yung JMA's approximate formula. So, the answer is 92.5 dB. And the answer sa textbook is 86 dB. Mayroong 4 dB na, kumbaga, margin. And sabi ko sa inyo kanina, yung ginawa kong formula is not considering yung mga losses. Yung approximate formula na ginawa ko is ideal. Hindi masyadong pinagtutuunan yung mga losses. But if we will try to, kumbaga, integrate, kung ipipid natin yung losses doon sa ginawa kong approximate formula, so 92.5, if I will consider the losses, in this one, may antenna pointing loss, na hindi naman typical yan sa mga problem. Kaya pag ibabawas ko yung pointing loss na 1 dB, and then there's an atmospheric absorption, which is 2 dB. So, minus 2 dB. And then there's a feeder loss, which is 1 dB. So, minus 1 dB. So, yung approximate formula natin na from ideal conditions, ibabawas na natin yung mga miscellaneous losses. So, the answer is 88.5 dB. And that is now closer doon sa 86.1 dB na sagot doon sa textbook. So pag nakakita ka ng choices, most probably, makikita mo na din yung most probable answer. Kasi malapit na yung sagot natin, which is 88.5, 86 dB, mga 2 dB na lang yung margin. Yan yung sa isang textbook. Still, applicable pa din yung ating JMA's shortcut formula. 2 dB lang. Yung kanina, almost 1 dB lang yung pagitan eh. Now, solve naman natin ito. Ay, medyo bumalik yata tayo. Ito yung last question. So, this is the last question. Galing naman ito syempre, sa superbook ko. So, this is from my superbook. And solve natin yung number 19. Calculate the carrier to noise density at the Earth receiving station from a satellite transmitting an EIRP of 49.5 dBW on a frequency of 12 GHz. The Earth station antenna angle of elevation is 7 degrees and the receiving figure of merit is 40.7 dB. Ito na problema. Yung mga previous example kanina, if you notice, given yung distance between the satellite and the Earth station. But in this case, ang given dito is the angle of elevation ng Earth station antenna. Balikan muna natin yung concept ng konti. Ito yung mundo, and then meron tayong tinatawag nating geostationary orbit or geosynchronous orbit. And tuklasan nila, if you place an object 36,000 kilometers away, approximately 36,000 kilometers away, it will orbit the Earth, iikot siya sa mundo natin kasabay ng pag-ikot ng mundo. Kaya nga ang tawag natin is geosynchronous or geostationary. As if, pag nasa mundo ka, yung object na yon is as if it's stationary. Kaya nga ang tawag natin sa kanya, geostationary orbit. So that orbit is more or less nasa around 36,000 kilometers away. And now, if you have an Earth station, ang closest distance o ang satellite natin will be closest doon sa ating Earth station if the Earth station is directly above the satellite or if the angle of elevation is 90 degrees. Ito yung formula to compute for the slant distance o yung distance between yung Earth station antenna and the satellite. And the distance is equal to negative r, then sine ng beta. Beta is the angle of elevation in degrees, plus the square root of r plus h, quantity square. Yung h natin is the satellite height in kilometers, and r here is the Earth radius, so which is equal to 6,400 kilometers. Sa ibang mga book, if you want exact value, that's 6,378 kilometers. Minus yung Earth radius square, and then cosine squared ng beta o ng angle of elevation. Now, kapag sabi natin kanina, pag nagpa-pile up na yung mga formula sa utak mo, kahit napakasimpleng formula, medyo burden na yon. What more kung itong formula na ito? Distance is negative r sine beta plus square root of r plus h squared minus r squared cosine squared beta. Naku, ang bigat niyan. Ang bigat niyan sa memory, kumbaga sa computer. Parang Chrome ito. Parang Google Chrome. So, ang hirap niyang i-absorb pag masyado na madaming laman yung utak mo. Now, itong given problem dito, yung ginawa kong problem is, merong angle of elevation. Sabi ko kanina, kapag ang Earth station is directly above the satellite, so pag ang ating beta is 90 degrees, mawawala lahat ito, wherein D is equal to, magiging R na lang yan. So, which means, yung ating, o magiging, tawag dito, yung 36,000 kilometers na lang po yan. Yung height natin, the closest is, when the Earth station is directly above, that's 36,000 kilometers. And the farthest is, kapag naman nasa horizon na halos yung satellite, or when the angle of elevation is 0 degree, or 0 degrees. And ang distance natin doon, that's approximately nasa 42,000 kilometers. Kasi mawawala itong part na ito, itong sine beta na ito. And yung cosine ng 0 degrees is 1. And then this one is 6,400 square. And this one is 6,400 plus yung 36,000 kilometers. You square this minus this one. So you take the square root. That's approximately 42,000. So yung satellite natin, mula sa pinakamalapit, which is 36,000, hanggang sa pinakamalayo, which is around 42,000 kilometers. But in this case, ang binigay is, ang angle of elevation is 7 degrees. pwede nyo i-compute yan. Given naman yung formula dito eh. Paki-feed lang yung value ng angle of elevation, makukuha nyo yung distance, at pag may distance ka na, makukompute mo na yung free space loss. Pag meron ka ng free space loss, makukompute mo na yung carrier to noise density. So, ang carrier to noise density natin is yung EIRP and then yung free space loss plus yung G/T and then yung baka makalimutan mo yung Boltzmann's constant, yun pa ang problema. Kabisado mo na nga lahat, then nakalimutan mo yung Boltzmann constant. So now, using the approximate formula, using my approximate formula, sabi natin, tatlo lang yung kailangan mo tandaan, yung EIRP, and then yung G/T, and the constant. So the EIRP in this case is 49.5. Hindi ko na ipapakita yung long method. Haba pa yung time natin eh. Plus, ang FOM niya is 40.7. So 40.7. And then, since ang pinapahanap is carrier to noise density, anong constant natin? That's 25 dB. So I'll just add plus 25 dB. So the answer is 115.2. Ang pinakamalapit dito, so hindi ako sure kung ito ba'y pass board exam. Hindi ko nalagyan ng tag eh. Kasi normally yung mga pass board exam ko is nakalagay kung anong board examination siya. So I'm not sure if this is a pass board exam question, but take note of the choices. A is 11.2, and then C is 112.5, B is 151.2, D is 100 dB. Ang sagot natin approximate is 115.2. And the closest is definitely letter C. So, kung gusto mong isolve yan ng mahabang method, i-check nyo, i-verify nyo kung ang lalabas bang tamang sagot ay 112.5. But ang sagot natin is 115. So, pag ito'y lumabas sa board examination at nakita mo yung tanong na yan, nakalimutan mong ano yung formula ng distance, yung negative r sine beta plus square root of r plus h squared, etc. Nakalimutan mo yon sa sobrang kaba mo. Yun pa yung kalaban mo sa board examination eh. So, ang pinakamalaking kalaban mo is yung kaba. Kahit na gaano ka pa kagaling, pag kinabahan ka na, eh yun ang delikado. Kahit yung mga basketball player, kapag halimbawa, pressure na, ilang segundo na lang, and then ikaw yung mag-free throw. So, pag naunahan ka ng kaba, eh kahit gaano ka pa kagaling, pwede ka mag-miss. In this case, pwede mo makalimutan yung formula. But using the approximate formula, kung meron kang backup, o mas maganda ito talaga yung primary mo, yung approximate formula using JMA's shortcut, pag carrier to noise, minus 36 dB, pag carrier to noise density, plus 25 dB. So in this case, carrier to noise density, the answer is 112.5. Ang sagot natin is 115.2. So that is for this particular episode of Hacking the ECE Board Exam Series. I hope makakatulong ito sa mga magte-take ng board exam in the future. After this pandemic, sana makatulong siya sa inyong magte-take ng board examination. Ang next na plan kong i-discuss is patungkol naman sa fiber optics. I want to dedicate more time. Madami kasing pwedeng computation sa fiber optics na pwedeng lumabas sa board examination. So I want to dedicate a series for fiber optics. And then, yung iniwan kong question doon sa Facebook page ng Keymaker, kung nakita niyo yung question na yon. So you have two fiber. Yung dalawang fiber, ang cladding niya is 125 microns. Standard naman yun Yun yung typical cladding diameter. And then, yung sa isang fiber, ang core niya has a diameter of 8 microns. Kung tama pagkakatanda ko. Yung core niya is 8 micrometer ang diameter. Yung kabilang fiber, ang core diameter niya is 50 microns. Sa madaling salita, we have two fibers na yung isa, ang core is 50 micrometer at yung isa is 8 micrometer. Ang question ko doon na iniwan is, which of the two fibers, which of those two fiber will gather or will collect more light kung pag-uusapan natin sa optical communication system. So, I'll discuss that sa mga susunod na topic ng ECE Board Exam Series. So, stay tuned dito sa ating series na ito. I'm planning na mag-discuss pa ng iba pang mga topic. So, doon sa mga walang budget na mag-review sa review center. So stay tuned. I'm planning na for this 2021 is mag-upload, especially for fiber optics, plano ko na medyo habaan ng konti yung discussion. Mag-discuss ng medyo mas madaming detalye about sa fiber optics. So yung iniwan mong tanong, which of the two fiber, yung may 50 microns na diameter, assuming same source of light, using same transmitter, using the same laser, which of the two fiber, yung may 50 micron na diameter, o yung mayroong 8 micron na diameter. So that will be our topic for the next ECE Board Exam series. So again, thank you for watching the series, and if nagustuhan niyo yung series, please kindly subscribe sa channel, and please support the channel by sharing the videos sa Facebook, and then also follow the Keymaker page sa Facebook. So thank you, and good luck sa mga magtitake ng board examinations sa this 2021. And again, thank you guys. I'm Jason Ampolacchio. This is Keymaker channel. So goodbye mga ka-wavelength.